Okay. So, first of all, thanks to everyone for coming to see this presentation and for the hosts to invite me. My name is Dimitry Leskov. I work for a company called Excelsior in northwest Russia. And I'm used to be a software engineer, but later moved on to technical support, the sales engineering, and marketing. So right now I'm the director of marketing for my company, but I still occasionally program. And I used to write compilers and moved on to sell them. And the company that I work for is a small independent software vendor based, as I said, in northwest Russia. It's focused primarily on programming languages and on tooling. And we have specific interest in the Java technology. We've been working with the Java technology since the last millennium, I would say, so it's the late 90s. Yeah. And in the year 2005, we became a Sun Java licensee. Now we are Oracle Java licensee. And our main product is actually a JVM. It's called Excelsior. First of all, before we begin discussing the topic, which is ahead of time compilation of Java, let's agree on terminology. There are some misconceptions and misunderstandings about what a compiler is and what are compiled languages and so on. And I just want to make sure that we all agree on the terms, the names of things. And there is actually no such thing as a compiled language or interpreted language. Some people would say that C is a compiled language and say Python is interpreted. But in fact, you can write an interpreter for C and you can write a compiler for Python. And traditionally, what was meant by the word compiler was a program that takes the source code as input and produce executable binaries that runs directly on hardware as output. But this term has blurred later. For instance, Java C stands for compiler, but it doesn't produce code that any particular hardware can run directly. At least right now nobody is making such hardware. So translator would be a better word for that. It's just a program that translates program from one representation to another representation. But somehow compiler is now used to define those things. And we'll discuss in this presentation not compilers that produce bytecode or some sort of abstract syntax tree that can be serialized to disk and later loaded for execution. Nothing like that. We'll discuss in the old meaning of the word compiler, native code compiler. So it's a program that takes as input something like source code and produce native code which can run natively on hardware. And that is why it's called native. So the JVM, Java Virtual Machine, takes as input Java bytecode, which is portable, which cannot run natively on any CPU or any processor. What are the options for executing that code? So one option is to interpret. And the first JVMs only had interpreters. And Java was very slow in its early years. And the technologies were developed to make it run faster through transformation of this portable bytecode into native code. And basically, there are two options, two major options with regard to when you make this translation from bytecode to native code. So one of them, which is used in Hotspot and many other implementations, is so-called just-in-time compilation or dynamic compilation. It occurs on larger systems that executes the application at application runtime. So the application is delivered in bytecode form to target systems, and every time on every system after it's started, it's gradually some pieces of it get compiled to native code. Another option, so-called static compilation or ahead-of-time compilation. In this option, the transformation from bytecode to native code occurs before execution. There are two sub-options here. It can happen on the developer system even before the application is deployed. So you get a normal conventional binary like Windows exe file or ELF binary for Linux, and it's then deployed to the target system and runs immediately directly on hardware. And the other option, which is actually implemented in the most recent version of Android Art, it's compilation at install time. So the application is deployed in the form of bytecode to the target device, and right after it's installed onto the device, it gets transformed into native code at this point. So, what are the differences between these major approaches? We will only consider the first two. In the JVMs that only has the just-in-time compiler, you basically get the source code, compile it into class files, and then package into jars, right? And that's what gets deployed onto the target system. This is a borderline between the developer system and the end-user system. So on the end-user system, these jars are first fed into an interpreter that begins executing the code. Then a profiler, which is also present in the JVM, detects methods that are called often, that are called many times, and also detects methods with loops that execute many times. And after certain thresholds, these particular methods are fed to the chip compiler, which produces native code. And that all runs on top of JVM with native methods, and which in turn call the operating system. So it's rather complicated structure. When you have an ahead-of-time compiler, you produce native executable on the developer system. So what you deploy is an executable, some native methods, and that all runs on the operating system natively. And you might ask that, wait a minute, Java can load arbitrary classes. I can have third-party plugins. I can have dynamic proxies. I can have accessors, whatever. My application can generate bytecode at runtime. How is this going to work? We basically have two options. We can either interpret those classes, or we can also have a just-in-time compiler, which would produce native code for those particular classes. But the major part of the application is going to be compiled ahead of time. So, what we'll discuss today is if it's possible at all to compile Java ahead of time. Will it still be Java after we do that? What are the conditions when we can do that, when it makes sense to do that? And what are the advantages of this approach? And the advantages, I will visit briefly, are protection against decompilers. It's better startup time, potentially smaller installers, potentially better performance, and these three advantages are especially important in embedded and mobile, and often on the desktop. And we also discuss if there are any advantages on the server side. There are certain myths around ahead-of-time compilation.
Can we interrupt you during the presentation?
Sorry?
Can we interrupt you during the presentation?
If you have questions, there are not that many of us to answer them.
Okay. That's a disadvantage, right? Because I understand that you compare that directly to native code.
We take as input, and when I say we, I mean we, the vendors, the makers of ahead of time Java compilers, not just my company. We take as input bytecode.
Okay.
So we don't take source code as a. We need to compile third-party jobs, right? So you don't always have source code for libraries, right? So
I understood that you compile Java directly to binary, right? So
no, it's not directly. It's actually we take jars as input. Oh, here you see. So you first get jars, then you feed them into a ahead of time compiler. Okay.
It's the usual way with classical languages, just as I'm thinking about BASIC or Visual Basic or C or Pascal or some other languages, some classic languages that they used.
Yes.
I don't know if the name was ahead of time compiler, but they were compiled before deploying the software. So.
Yes, as I said in the beginning, it's what the word compiler used to mean is actually what we now call ahead of time compiler when applied to Java or .NET.
Okay.
Right? Because Java and .NET and some other languages and platforms use bytecode as a medium for application distribution. Right? But it can be further compiled either at application runtime, just in time, or ahead of time on the developer system. So, historically, some microsystems vendor Java was pretty much against ahead of time compilation. They said it should be always distributed as bytecode, and it's write once, run anywhere, and so on. And probably because of that, there are certain myths and misconceptions about the very possibility to compile Java to native code ahead of time, as if it was C or C++. So I will try to dispel some of these myths. So the myth number one is that Java is too dynamic, right? With that reflection, how can you compile ahead of time? You don't know what is going to happen at runtime. You have JNI, and you have dynamic class loading an application may load a class that is not known to the developer. It may be generated at runtime, it can be a third-party plugin, and so on. So the question is whether static compilation or ahead of time compilation is possible at all in this case. So when it comes to reflection, it's actually just meta information. You can have names, identifiers associated with classes and variables in a language like C. You can just do it by hand. You can do reflection by hand, right? So you can have a table of identifiers, a table of class names, of variable names that will just produce a mapping between names and locations in memory. Right? So what actually happens with reflection when you compile Java ahead of time is it gets resolved into a pre-compiled class, as we'll see further down the road. And with dynamic class loading, as I already shown on this slide, any third-party jar or any class that is generated at runtime can be compiled just in time. And the point is that there are many applications, all classes of which, or the majority of classes of which, are known beforehand. Only a few classes, if any, get loaded generated or loaded at application runtime. Most of the application is non-static.
because for Java 8, when you compile the code, you have a type erasure. you need to compile the source code with the debug symbols enabled for the ahead of time compilation?
No.
No?
You can have, you don't need to do any special manipulations.
I'm saying because
because an ahead of time compiler takes byte code as input, so it doesn't give information about the types, right? So the types have been erased by JavaC, right? And that's the semantics. The semantics of the byte code is to work with types erased, right? So it's the JavaC compilers that care about types at this point. So you can break these assumptions if you do something via JNI and so on. So you just have options, right? And that's why you have things like array store exception. Right? So Java possibly may not let you assign something, but at the bytecode level you can do that, right? And you will get array store exception at runtime.
Another question. Does load time weaving work with that?
Sorry?
Load time weaving? So
What time?
weaving. So for instance, with aspect J, that you add a bytecode at runtime. Not runtime, but at load time, when the class gets loaded, it's a class loader.
Yeah. I will actually talk about placeholders, but as far as I know, at least some aspect-oriented programming tools enable you to do this bytecode manipulation before runtime. So if you manipulate bytecode only after the application runs, then of course you cannot compile those particular classes ahead of time because they're going to be changed.
I mean, I'm not talking about runtime, but load time, right? So there's the compile time weaving, the load time weaving, right? So,
well, if the bytecode gets changed when it's loaded,
that's a
problem.
Yeah.
Then we have a problem. Yes,
That's what I'm saying.
That's correct. Actually, we use aspect J
Okay.
in our own product, which happens to be written in Java and Scala.
Right.
And we just do that build time, this manipulation.
Yeah. Compile time.
Yeah.
But you have shown that there's a third method that is a hybrid method that you can use ahead of time compiling, also using for a tiny group of your product JIT compiler. So in that case, where you need to use the JIT compiler, you can use it, but in other parts of your product, you can also use the AOT compiler.
Yes, that's correct. So you have a standard library, for instance, right? So you have thousands of classes in the standard library. They are not going to be manipulated. Why compile them just in time? You can pre-compile them all, right? So at least these classes you can always pre-compile. Then how much of your application, what part of your application you can and cannot pre-compile? It depends on how you write. But our practice shows that many applications don't use these bytecode manipulation techniques at all.
You never know, because I may want to introduce an aspect that affects a library class. For instance, to monitor performance monitoring and stuff. So you never know what the aspect will modify, because it's everything that you have in the class loader, you know? You cannot...
Yeah.
Just asking, eh?
Yeah. I said that's a problem. You cannot always do that, right? So there are some limits. The other myth is that ahead of time calculation kills same bytecode as the other versions, but Windows JRE. Then you would separately download Linux, maybe 32-bit and 64-bit Linux, and again, there will be a JRE inside the package and the same bytecode. So, you cannot build once, package once for all platforms. When you want to have control over what JRE is actually used to run your application. You typically test on a particular version, right? You write against a particular version of the JVM. So you know that it runs on Java 7 or maybe Java 7 update 55. Right? That's the version you tested on. You don't want to deal with support issues stemming from the fact that your user tried to run your application on Java 8 or on Java 6 or on some update where it's known to be broken. Right? So you still make platform-dependent packages, platform-specific packages. So why not put the respective native binaries into these packages? Make them from your Java bytecode and distribute that to your end users.
But I think I'm missing. Is it compiled on the platform, on the platform it's being deployed on, or is it pre-compiled before?
It's pre-compiled before. It's pre-compiled before.
Okay, and can it be compiled dynamically on the platform that you are deploying from?
It depends on what the implementer chose. So our product, for instance, works on the developer system, so you pre-compile. With Android, with the latest Android, it compiles at install time.
And then we don't have the problem of distribution. Right?
Yeah, in the other case. But we have the problem of long install time.
And
Right.
tuning probably.
Sorry?
And if you want to tune something, you don't have any control about like
Tune for what?
like I don't know, like set some parameters for the like how you want it to be compiled. Like if the platform compiles a thing, you don't have the way of like controlling how it's being compiled. Maybe I don't know, obfuscation level or I don't know.
Yeah. I think if I'm getting you right, you're saying that or when you compile just in time or when you compile at install time, you know the specific hardware for which you compile. You can produce code specific to the hardware. Well, that's true for, but it makes difference for few applications. For if you have like number crunching application and you can it can use SSC, right? And if you have just in time or install time AOT, right? Then it can use SSC on the particular versions that are supported by this particular processor. But again, our practice shows that it makes a difference only for a small number of applications. Not many people do number crunching in Java on the one hand, and on the other hand, SSC, because of the Java specification, you cannot do many optimizations, many vectorization optimizations with SSC. Okay, so this third myth actually goes the other way. So some people think that, okay, if we compile Java ahead of time, then we can get a small executable. Right? So I have a 100 kilobytes jar file. If I had 100 kilobytes of C source, I would probably get some 100 kilobytes executable, and that's all. Unfortunately, that doesn't work. Mostly because of the standard library, because it contains many classes, thousands of classes, and it's not possible because of reflection. It's not possible to compute beforehand which parts of the standard library your application uses. You have to take all that library with you, even if you're writing just hello world. Right? And you also need other things that Java has, which C doesn't, like memory manager with a garbage collector, maybe several garbage collectors. You have reflection, you have JNI, you have threading and synchronization, and many other things. So Java runtime is substantially larger than C runtime. These are the overheads that you just cannot remove if you preserve the semantics of Java. So program compiled ahead of time remains a Java program. It needs a JVM to run. It needs memory manager, it needs a garbage collector, and so on. But that said, it's actually possible to leave out certain pieces of Java standard library when you build the installer without breaking the specification. You can read more about this techniques that we developed at this URL. I won't go deeper into this. We actually have a separate talk on this technology. And if you're interested, I will just invite you to read this material on our website. Okay. So, there were already questions from the audience on the next topics that I wanted to touch. When I said that Java is too dynamic in a myth, I actually lied. It's not completely myth, of course, and the problem is non-standard class models. In the general case, a class is not defined until it's loaded for the purposes of ahead-of-time compilation. I mean, it's not completely defined, and it gets loaded only at runtime. We don't know how to resolve references between classes if we don't know anything about the class load. We don't know how they create unique namespaces and so on. The class loaders, custom class loaders, are actually quite widespread. The most well-known system that relies on them is probably OSGI. And Oracle says that we're going to have a standard Java model system in Java 9. And it's also used in Java EE application service. It's used in servlet containers. For instance, in Tomcat, you have one class loader that loads Tomcat itself, and then you have one class loader for each application, for each web application. So how can we compile, how can we nevertheless compile such applications statically? So one option is to compile each class separately and do all the reference resolution later. Runtime, but this basically disables a number of optimizations that are very important for Java, for improving performance of Java applications, as I will discuss in more details a bit later. Or we can actually teach the compiler how some particular class loaders work. And if we have access to the source code, for instance, we have access to the source code of Tomcat or Eclipse RCT, we can study how they load classes, how they create these namespaces, and so on. And we can add a component to our ahead-of-time compiler, an import result that would analyze our jar files, knowing that these are OSGI bundles of an Eclipse RCT applications, or this is Tomcat, and these are the web applications deployed. And just by analyzing this structure on this without actually running the application, it can determine which class loaders will be created when the application will run, and which classes will be loaded by which just creates an instance of Java class, for the class, fills in the respective reflection information, and then the code is already natively compiled, and the operating system will load it automatically when the control gets passed to that. We actually have this technique implemented for two particular popular frameworks. For Eclipse RCP, so you can actually compile ahead of time Eclipse IDE, the entire Eclipse IDE, or you can write your own application based on Eclipse RCP and also compile it completely ahead of time, and its classes won't be needed at runtime. And we also have that implemented for Apache Tomcat. So you can also compile your web applications ahead of time, as long as you compile it all together. So why? Question?
Yeah. Actually, with the web application, I will need to build first my app server, and then build my web application as a native, or make something.
No. What you do actually is you have an installation of Tomcat. Well, in our case, we always support Tomcat at the moment. So you have an installation of Tomcat. You deploy your web applications onto it, into a web app directory, and then you simply point our compiler to that entire thing, and it will compile it all together. So you will get one binary that contains Tomcat and all your web applications.
So, for example, if I have a cluster of web servers or containers, I can actually run these clusters natively in different machines.
Yeah. Oh, you will have problems with you won't have things like hotspot. You won't be able to replace applications and so on. But there are scenarios when it's not needed. I will actually speak about that in a minute. Okay. So why? The question is why? It's possible to do that, but why would anyone want to compile Java ahead of time? Hotspot is such a good JVM. It's been in development for well over a decade, and it actually produces amazingly fast native code for the application. So why compile it? So one unique feature of ahead-of-time compilers is protection against Java decompilers. You probably know if you do a web search for Java decompiler, you will get like half a dozen results for free, decompilers that you can feed your class files to, and you will get almost the source code back, almost the original source code back. The only thing that gets erased are the names of local variables, right? But you will get the names of classes, you will get the same structure of classes, the same structure of methods, and so on. So Java is very easy to, Java apps are very easy to decompile if you distribute them in bytecode form and don't do anything to protect them. What you can do to protect? You can use obfuscation. If you use name obfuscation, however, it breaks reflection in the general case. And if you know the particular classes that gets loaded by reflection, or the particular fields that get accessed by reflection or via JNI, you need to build exclude lists for your obfuscator so that it doesn't change those names. But this is quite error-prone and fragile technique, because if you make any refactoring, any changes, any renaming, your exclude list may get invalidated. And then you, or what is much worse, your end user will get a not plus the found error at runtime in production. And even if you obfuscate the code, you can also obfuscate the code some decompilers might break, and so on. There are still hints remaining about the purpose of each particular decompiled class, right? One of the reasons is you cannot obfuscate RTJAR file and any references to it. So if you have like 10,000 classes in your app, but only, say, a dozen has to do anything with JavaX security, anyone who gets access to your bytecode will be able to identify those classes and study them, even if it will be more expensive to do that because you obfuscated them. But they won't need to study the entire application to find out where you do something with encryption, right? And maybe they won't even need to understand what your classes are doing, but just put your application into a debugger and set some breakpoints and intercept the data. Maybe find out the private key that your application is using to communicate with your server and so on. Whereas, if you compile your application down to machine code, you get one solid binary, which you can only feed to a disassembler. There is no decompiler that will produce Java source from it. Right? And you won't be able to easily recover the structure of the application because the code might have been reordered. And because of optimizations, you actually won't be able to restore code because some information will simply get lost in optimization because it's not essential for the semantics of the program for correct execution. And optimizing compiler will simply discard this information. You won't be able to recover it from it. I'm not saying that this completely disables any reverse engineering attempts, but this ahead of time calculation certainly makes it more expensive to decompile, to reverse engineer your application compared to distributing it in bytecode. This is actually a unique advantage of the AMT approach. The other advantages are conditional. You may or you may not get them. It depends on the application, but our experience shows that you can often get improvement in application start. If you run your application after you boot your system, you will notice that it takes a while to start if it's a large Java application. But if you terminate and start it again, you will notice that it starts much faster. So it's cold start versus warm start. Warm start is much faster. Why? It's because actually what dominates the start time is I/O. It takes time to load all the classes from this, right? And they are loaded in scattered order, not in a particular order, not sequentially. So you get this class from this jar, then that class from that jar, then something from RTJAR, and so on. So it's very scattered. Right. But on the next run, it's all in this cache, and it starts much faster, simply because the system doesn't need to read into a random access memory again. So they are already there. So if you ever noticed this process, JQSZ, you might wonder if it's a virus or something. It's actually an acronym for Java Quick Start. It's a small process that is installed by JVM on Windows systems, and all that it does, it from time to time, when the computer is idle and not running on battery, it reads pieces of RTJAR and reads JRE TLLs from disk. So they get loaded into this cache, and if at some point you decide to start a Java application on that public JVM, it will start much faster because, specifically because of this. Because some parts of RTGR and DLLs will be in this cache. I'm not sure if it's still present.
In the division of time.
In the current JVM, not used to for some years. But the question is whether AOT is really fast. Java bytecode is relatively high level, and it's more compact. It's smaller than the equivalent native code. So native executable can be 2 or 3 times bigger than the original one. And it will actually take more time to load. So how can AOT be faster? Simple trick. We can profile the startup. It's rather easy. We can easily automate it. And we can see which classes get loaded at startup and in what order. And we can then feed this startup profile to the head of time compiler. And at loop time, it will place the code that is executed at startup near the beginning of the binary, of the resulting binary. And moreover, the very first thing that the binary will do when it starts, before any other initialization takes place, before Java code gets executed or JVM loaded, it will simply touch the pages of the executable, so of that part of the executable that contains the code that it gets executed at start. And these pages will be loaded by the operating system into memory, into this cache. And then when control will pass to the part of the executable, it will already be memory. And our experience shows that for a fairly big Java application, you can get like 2-3 times better startup time, better code startup. And I actually have a sample here. These are 3 applications that provide about the same functionality as RSS readers. FeedDemon and FeedReader are native applications written in C++ or something. And RSS all is written in Java. It's actually an Eclipse RCP application. And as you may see, if you use a JRE, the cold startup time is much worse, especially if you run on battery. The blue bar is cold startup when the laptop is running on battery. But if you compile it down to native code and use the standard optimizer, you get about the same startup times as the native applications. Performance. Performance is probably the most controversial topic. Historically, when Java was young, so it's like late 80s, it was interpreted, it was quite slow, and there were several ahead of time compilers at that moment that really made it fast. And there were like half a dozen different products, quite expensive, but because Java was already making its way into enterprise, they found their customers. Then in 1999, Hotspot was introduced, first sophisticated just-in-time compiler for Java, and most of those products disappeared because performance became good enough. And a couple of myths surrounding this topic that AOT is faster because if we compile statically, if we compile ahead of time, we'll get something that we will get from C. And C is faster than Java, so we will get faster applications. The truth is that Java has certain overheads. In C, if you try to access an array past its end, you get array out of bounds exception. In C, you get segfault or you get memory corruption if you write past that. And in Java, there is an overhead, a runtime check for array bounds, and so on. Java has more sophisticated memory manager, garbage collector, which also has their overheads and so on. So, in the general case, even natively compiled ahead of time Java program won't be faster than the equivalent C program. And on the other hand, people argue that just-in-time compiler gives faster code because we got dynamic execution profile, as you mentioned. We get the possibility to optimize the particular hardware and so on. But let's see what the compiler can really do. So these are just some of the optimizations of the So these are just some of the optimizations that the compiler can do. And some of these optimizations are quite important for an object-oriented languages like Java. And let's see if just-in-time compiler can do all of them. Because, as I said, Java is object-oriented language, because of the common style of writing programs, you've probably seen stack traces, which like 100 of methods or maybe 200 of methods. So there are many methods calling each other, and most methods are actually small, otherwise there won't be many of them. So, for example, we have many getters and setters and so on. And by default, the methods are virtual in Java. So unless you mark a method final, and I bet you seldom mark methods as final, they're going to be virtual. And if you have virtual calls, how can you actually make inline substitution? How can you take the body of the method and replace the call side with the body of the method? It's very important optimization because calls have big overheads associated with them, big CPU overheads. So, if you have a dynamic compiler, you can make speculations, to make speculative assumptions that if at this side that method will call, the next time we use this side, most likely the receiver will have the same type, so the same method will call, so we can simply add low-cost runtime check for that, or we can just remember this assumption, and if this method is not overridden at the moment, then we can always call it directly. And if some class gets called as it overrides that method, we can simply invalidate this code and let the interpreter interpret the method and maybe possibly compile it just in type code. But with the two other approaches that we can do, we can analyze the class hierarchy, and we can also analyze types. The simplest type analysis is shown here. If we create an object of certain type T and then immediately call a method from this object, we know which particular method gets called. Even if some subclass of T overrides this method, at this point we know that this call is not virtual. In the more general case, we can check, we can analyze the entire class hierarchy, and we can insert runtime check if the runtime if some class was loaded later that we didn't analyze, and it may have overridden that method, then we fall back to a virtual code. Similarly, with type analysis, suppose we have class A and two subclasses B and C that don't override the method foo. If we have an operator that creates an object of one of the two subclasses, and we know for sure that foo is not overridden in B and foo is not overridden in C, so it's the same, then this call is actually not virtual, and we can enliven. Well, this is not a pattern that you would often see in programs, like based on some condition, create an object of this type or an object of that type. So in the more general case, you might use different methods to create an object of the base type. Again, if we can determine that method bar returns all the instances of B and buzz returns all the instances of C, and this assumption holds that the method foo is not overridden in B and not overridden in C, then again we can inline the call of foo. But how do we know what this method is? We do global analysis. If we can analyze all methods of the application, all classes, all methods of the application, we can compute a lot of useful information about it. And then that information we can use to optimize each particular method. But this optimization is very expensive in terms of time and memory. So it takes a lot of time to analyze all classes, and it takes a lot of memory to hold all this information. In fact, in our implementation, we even have to dump to this. It doesn't fit into the memory of a typical developer system. And another useful optimization that we can do is stack allocation of objects. As you know, the primitive types in Java are allocated on stack, local variables, but all the non-primitive types, the instances of all classes, get allocated on the heap. But many of them actually temporary objects that get allocated, that are local to the methods in which they are allocated, that don't the references to these objects never get into any global, into any static fields or elsewhere, into any global data structures. And such objects can be allocated on the stack and then tested together. And there is an analysis, it's actually implemented in the later versions of Hotspot, called escape analysis. It determines whether an object escapes into shared memory. And let's consider an example of how all this can work together. Let's say we have a rather typical iteration on collection. So this is the original source code that you might have written in Java, right? This code is just a syntactic sugar for this code. So we get collection, get an iterator over the collection, and then we use the iterators methods as next and next to retrieve objects from the collection and call the methods do something. So this and this are absolutely equivalent. if invitable. So, suppose we know that the collection type is array list. Then we can transform that code like this. So we have a local variable list of type array list, and then we basically have the same, but we know the type from global analysis. So this is equivalent to iterator, not of interface type iterator, but of particular class, which is class local to array list, inner class list iterator. Then we can notice that this variable iterator never gets passed anywhere. We can understand that has next and next don't pass their receiver, they don't pass this anywhere, so it doesn't escape to the global scope. Nobody will ever have a reference to this iterator except this full method. So what we can do is we can actually allocate iterator on step. We can inline its constructor. Then we can inline the methods hasNext, which just compares whether the current position is still less than the size of the collection. We can inline the method next, which basically just increments the current position and returns the previous value. And then we can explode. This is called object explosion. So we still had iter object allocated on stack, but we don't ever refer to it as an object anymore. We only refer to its fields. As you know, we refer to the field cursor, we refer to the field size, but we never refer to iter. So we can explode it. We can replace its fields with with respective variables of primitive types. And so our original example is actually equivalent to the following, if you know that the collection is an array list. Or, if you wish, we can transform it into a formula. So instead of calling hasNext and next on each element, we can simply iterate over an array containing the collection data. But you need to do tape analysis, you need global analysis in the general case to implement such optimizations. Moreover, this analysis and optimizations are...
I would say that this analysis is kind of impossible if you have like third-party libraries that are into the class pool, right? Because you have like classes that would extend from the main classes that you don't know about
feed it all. And the compiler analyzes it all. Only if there is some class that you did not feed for some reason to the compiler. For instance, you can say, okay, this jar I'm not going to compile ahead of time because I want to be able to replace it at runtime, right? Or you can say, okay, my application can load a third-party plugin, right? Or it can generate something, some classes at runtime dynamically. Yeah. Then you will actually have this part.
Yeah, always the else.
Yeah. So you will have so basically what you would have in that example, if the runtime type of A is array list, then we can do a for loop. Otherwise, we don't know what is this collection. Do a virtual code. Makes sense? Okay. So the point I was trying to make is that these optimizations and analysis are often quite complicated, and they are also iterative. For instance, if you make an inline substitution, you then analyze the method. Your analysis of the resulting code may determine that some pieces of it are never reachable. So you can constantly evaluate certain conditions. You can determine that certain sections of your code in this version into which you inline certain methods never get executed. That code will be removed, and you will have more budget for inlining. So you can inline more code. So typically, these optimizations repeat several times until some stable code is found. And the other thing is that for any tricks like that, you need to analyze the entire program for effectiveness. And the just-in-time compiler simply cannot afford this weight. Now, on the other hand, speaking about the advantages of dynamic compilation, you can do profiling, you can do selective compilation, of course. Hotspot doesn't compile everything, it compiles only frequently executed methods or methods with loops that executed many times. You can do inline substitution only of those methods that are worthwhile substituting inline because they also get called often. You can do execution trace optimization and so on. You can select optimal instructions, like SSE, for instance. But the problem is some applications, especially graphical user interface applications like Swing. Typical Swing applications will have many methods that are slightly warm, so they don't get called too often to trigger the just-in-time compiler. They remain interpreted. And even if they eventually get compiled, the next time you start the application, all this information will be discarded and they will be interpreted. And what we can actually do is we can combine these two approaches. This is not something we already have implemented, but this is possible. You can collect the execution profile and you can feed it to the ahead of time compiler and make a build taking this information into account. In fact, C compilers have this capability for at least 19 years now, because 19 years ago I worked with a C compiler that could do profile-guided optimizations. This leads us to an idea that ahead-of-time compilation can be possibly useful on the server side too. Because if we applications that say runs on a cluster that has many computers, we can compute the execution profile because it will stabilize at some point. We'll know which classes get loaded, which method gets executed often, and so on. We can have a dedicated server in our cluster that would simply take this information and compile well, ahead of time and just in time the application. So the application will keep working on JVMs with just-in-time compiler, and in the background, one server, one dedicated system will produce a version with the optimizations that only possible in the ahead-of-time compiler, and then gradually replace them. It's a rather old idea. We haven't implemented it yet, but it's possible to do such a hybrid thing. Okay. So, but in general, on a server, you have plenty of resources. You have plenty of memory, you have many cores and so on. Whereas on embedded system, the situation is exactly reverse. If you have something like a smart card, your only option is interpretation. You can only have an interpreter there. So a Java card has an interpreter. But if you have something a bit more powerful that can potentially run normal Java MCDC or full-blown Java C, it's still going to have less computing power than a typical desktop, let alone server. So on the embedded, the advantages of ahead-of-time compilation are emphasized because on each and every device you don't have to spend the precious computing power on producing native code for your application or optimizing your application. And a special case of embedded devices is mobile. So if you want to put a JVM on a mobile device, you will need to pour the platform classes there, you will need to put them into flash memory on your device. You will need runtime with garbage collection, with memory manager, you will need to support reflection in JNI and so on. So these are all overheads, overheads, and overheads. You will need a just-in-time compiler most likely if you want to have decent performance. And something is missing here. What's missing? It's a child. The just-in-time compiler is a program. It needs computing resources to execute. It needs memory and it needs CPU, and it will be spending the battery. Why compile an application on your mobile device every time it gets started? And it seems that Google has got it a bit earlier because, as I mentioned, in the latest version of Android, you get install time ahead of time compilation. The problem on iOS, on iPhone and iPad devices is a bit different. It's actually just-in-time compilation simply prohibited that. You cannot do just-in-time compilation on iOS devices. The only exception is the JavaScript engine in the browser. But any other application either has to be native compiled or it has to use interpretation. So the only way to get fast Java on iOS is to use ahead-of-time compilation. And there are actually more Java you get Android Java, but you can write for iOS and Android basically the same thing. There is codename 1, which is a commercial product, but also IBM. Not many people know that IBM has AOT in the J9 virtual machine. Some builds of Java from Sun actually used to have, again, these are commercial builds, used to have a head-of-head compilation. And Android, I already mentioned, that the latest version of Android has this art feature with install time and head-of-time compilation. The GCJ used to be the leading AOT compiler, but after Sun made Java open source under the same license, under the same GPL license, it basically stopped, so they only support Java 1.4 and Java 5 partially. And there is also a product, Jet, which is available for desktop at the moment. We have versions for Linux, Windows, and OS X, but we are going to move to mobile as well. So this is it's already reached version 10. It's been around since the year 2000. It's pretty mature, I would say. And these are the companies that decided that they need, at least for some of their products, they need AOT compiled Java. This is a partial list of our customers. And this is actually a screenshot from a screencast from the recent Java 1 from in San Francisco, the top Java conference produced by Oracle. And this is Oracle keynote that mentions AOT in JDK9. It's been considered. Of course, they have this, safe harbor statement.
It's going to give bullshit to the Java 10.
Yeah, so maybe it will never become a reality, or maybe it won't be in Java 9, but will be in Java 10, but at least it's no longer ruled out completely as some used to. So basically what I try to communicate to you today is that AOT compilation is possible. Native ahead-of-time compilation of Java applications is possible. That it does not break compatibility in the specifications. We can support all features and still compile ahead-of-time native code. Even if you have no standard class loaders, you can often work around this limitation by using Ngen resolver. The unique advantage of the AOT approach is protection from decompilers, but you can also often get better experience. You can get smaller installers, you can get better standard, and get JRE, and you no longer need the JRE, you no longer need to package it with your app or requires it to users and so on. On lower end systems, especially, you can get performance improvement, and you conserve power disk, and basically that's it. That's all I wanted to tell you about, except if you want to ask us.
Well, thank you for the presentation. It's interesting. Do you see a pattern of companies using like the hotspot for development and your JVM for production, for instance?
That's exactly the case.
That's the case, right?
That's the case.
We're living in a world where productivity is a must. I mean, we have like JVM, like spring-loaded, all these tools which rely on front loading of classes like class loader, right? Which doesn't work with your solution.
Yeah. Well, actually, there are two things that I want to emphasize. So, first of all, this Java compatible sign that we have, it's here for a reason. We are a licensee, as I said, and you can only become some Oracle Java licensee if your solution passes all the compatibility tests, basically, right? The TCK, so it's like 200,000 individual test cases, and we had to make our product pass all of this to become a license. because we realize that we can use the source code commercially, the source code of Java. So the standard library in our product is actually Oracle code. 99.99% is the same code that Hotspot standard library. Okay, that's one thing. The other thing is that we position our solution as more as optimization and packaging and deployment solution. It's not something that every developer would need on their workstation, not something that they would use all the time. So you would typically set up project file and then you would just put it on build server so you can get nightly builds, native builds. So you continue using the same tools, you continue debugging in your favorite IDE, you run on Hotspot and so on. But when you want to ship it, or maybe make a better version, or maybe make a demo, and you are concerned about your prospect, reverse engineering your application and so on, you can compile it down to native code and give it. We actually have an interesting server-side usage scenario that we even didn't think about ourselves. So one of our clients uses our product to protect the server-side code. You might think that why would you protect the server-side application? It would typically run in a controlled environment, and if you have someone access that environment, then you get a much bigger problem. But what the customer does is they make a certain application that they put on Amazon machine image in AWS. And when they have a prospect, they simply give the ID of that machine image. So the prospect can simply make an instance on Amazon in the Amazon cloud and run that application, the demo of that application. And because it's natively compiled, they are not worried that the customer will, not the customer, but the prospect will disassemble, the reverse engineer that application. So we didn't even think about this huge scenario. So we didn't think anyone would want to protect server-side apps. But there are cases where we will do.
So your main customers are basically companies that have a product that's give it to the customers. That's it, right? So it's not like I have a company and play my web app to the server, that's it. So that's my own product. It's more like customers or
Mostly it's desktop. I would say mostly it's desktop applications that are not always these are applications that we would distribute freely. I mean to everyone. It's not like all these are just demos, but some companies are just concerned about their intellectual property, even if it's an application for internal use, because it may be running in the field. Like people would carry some apps on their laptops. So the other scenario I can think of is we have a customer in the US, which is basically a large telecom equipment manufacturer. They have a solution for video conference and enterprise solutions that companies would install in their distributed offices worldwide. So it's for very large companies. And they had a special application that inspects the prospect's network and says if that solution can run on that internal network, on the intranet, or something has to be changed. And that application contains code that contains some trade secrets, basically. So it has some pieces of this big video conferencing solution in it. And engineer with a laptop to the prospect side, which can be on the other side of the world. And then they want our solution, compiled it to native code, and they simply let the prospects down. So that they said that our product paid back on the first trip that they did not have to do. So they did not have to send an engineer to the prospect side.
Two questions. One is related with from developer view. What happens when I have a problem? I got normally a stack trace. What happens with an application that is compiled to native?
You get a stack trace?
The same one?
Yeah.
Okay, so I don't have to understand from the developer view that I need to convert anything to.
Well, it can be a bit more sophisticated than if you had.
Suppose that my application breaks on production. I actually ship the application as a native application. What happens with this problem that breaks the screen? I got that.
Well, you basically get the same output that you get from bytecode version. So you get the same stack trace with names and such. So you can inspect it and whatever. You can do a test build with some debug, or you can have some debug features or some logging features that are normally not activated, but can be activated using system properties. And you can pass system properties to a natively compiled application.
But how is it that you get the same stack trace? I don't get that. But isn't it compiled to native code? And aren't the namespaces, aren't they erased afterwards?
No. You need the names because you still get reflection working.
Right,
Okay, so all this information is actually present in the binary executable. So you can deconstruct the stack trace. It uses a different mechanism for that, but you can restore the stack trace.
But on one of the slides you said that you can decompile the Java bytecode and search for the occurrences of Java security these days. Would you be able to do that in that case?
Okay, you will have a single table saying Java security, but you won't be able to understand easily to which places, to which place in native code.
Okay, because it will not correspond to the class.
Yeah.
Okay.
It will correspond to the place in code that is the code of the security class itself. Okay, but the reference from the client of the security class will be more obscure. So you can argue that this is security through obscurity. Right? So the information is there, but it's more difficult to recover. It takes more time and it takes more sophisticated, more knowledgeable engineering. Right? It's not like everyone can download the Java decompiler and run it against a class file, right, or a Java file. But here you have to be more knowledgeable.
And the other question was, you didn't find any problems with antivirus software?
With antivirus?
Yeah.
That's a very good question.
Because
we have to work to participate in the whitelisting programs.
Okay.
So every time we release a new version, we have to submit to Kaspersky, McAfee, and Norton, and so on. But what they actually detect most of the time is actually compression library, not natively compiled Java code or anything, but the compression library in our installer, which do you know 7zip?
Yeah.
The LZMA algorithm, which it uses, is available in source code form. It's like public domain or something like that. And some installers use it, and we also use it for compression because it gives very good compression. And many malware authors use it. so we can fall back to zip, to normal zip. So it can happen that you will get an installer that will trigger an antivirus, and then you make the exact same binary, package it not with other domain but with regular zip, and it will not. We've seen that, observed this behavior more than once. So it just coincidence.
Every time we use AOT compiler, we will produce a native executable file, including our code in compiler, and also all the JRE compile also, and third-party libraries, all included in that exe file.
There are two options, specifically in our program. There are two options. So by default, what gets compiled together is your application classes and third-party libraries. But the classes that constitute the standard library are already pre-compiled into DLLs on Windows or into dynamic libraries on Linux or OS X. And they are packaged together, but they remain separate.
Okay.
And there is also this global optimizer mode, which is currently not available in the 64-bit version, only 32-bit version supports it. But there you compile all the classes together. The standard library classes compiled together with your application and with third-party libraries and with, I don't know, OSGI or Tomcat classes. So all into one big executable. All the native method DLLs returns it.
In this second option, it's more like a portable application. So I can copy that file and move, and I don't have anything to stop.
You don't get one file.
Okay.
The problem is that the JRE has also certain DLLs, and it has some data files. So it has fonts, it has time zone information in many separate files, and so on. And this all, in the current version, these all files remain separate. So what you can do, and I have a blog post about this, you can actually package this together, all this together into a self-extracting executable. And specifically with 7zip, you can make it extract into a temporary directory and run from there. So in that sense, with the use of some third-party tools, you can get a single exit, but we don't support this mode of operation in our product yet. We get requests for it, but it's not very high on the priority list.
Okay, so it would be difficult to run 3 or 4 applications in different versions of Java all at the same time.
Several applications.
Several applications, every one compiled using different
Java version.
Yes, in the same machine.
It's quite possible. It's basically the same way you can do it with private JRE, this hotspot. So you just have a separate version of the JRE for each application, for a particular version. And same here, so you get the DLLs. They actually name differently, so even if you put them into the same folder, which is not recommended, but if you put them into the same folder, they won't get mixed. But it's not recommended, it's fragile. You simply have to install each application in a separate folder, and it will have its own copy of a particular version of Java
work as they run as a isolated systems.
What happened? Sorry about that. What happened with with the protocol that AMI, exactly. AMI, right? Yeah. That help, that helps connect.
It works.
It works.
It's part of the TCK, so it works. It's just based on reflection, and reflection works. So you don't really have to do anything special. There are scenarios when you have to do something special when you have third party. When you have some libraries with native parts. But again, this is a standard mechanism. So you just set standard property Java library path to point to the folder that contains this native DLS. Just
I have a question regarding performance. I assume you said it's not guaranteed that it would be that it is faster, but
it's not guaranteed.
Yeah, but
we have reports both ways. So some prospects say that their code is like 2 times slower if they use our compiler, and some customers say it's like 2 times faster.
But how can it be slower? Why?
One reason is that we have not yet implemented some optimizations in the 64-bit version. So the 64-bit version was released just last year. So it doesn't have the global optimizer, for instance. We simply haven't ported it. So it's less sophisticated than this. And the other thing is sometimes the application may have some very hard methods, so where most of the execution time is spent, most of the CPU time is spent. And hotspot just happens to optimize the method they need.
But don't you have the access to the source code of hotspot?
We do, but we cannot use it. It's totally incompatible with our Well, yeah, we can use it from a legal standpoint, from the license standpoint, but we have no use for it because we have our own compiler that has its own internal representations and so on. And in fact, there are applications where you won't observe much difference. Let's say you have an application that spends most of the time doing I/O, like the database requests. Let's say you spend 80% of the time not in Java code, so only 20% is in Java code. Even if you have a JVM that executes this code 2 times faster, you will only get 10% overall performance.
But if it is a swing application, would you typically expect increasing performance?
You don't mix performance and latency here. Okay, so you will likely have better response time with AOT compiled graphical user interface.
Because the hotspot would not optimize.
Yes, because all these handlers are executed only like 10, 20, 100 times, and the default threshold, if I'm not mistaken, is 2000 for to trigger compilation.
What about memory consumption? The typical issue about Java, the memory consumption.
It's about the same in general. So we don't compress data, right? So if you allocate billion an array of a billion integers, it's going to need 4 gigabytes, right? Whether it's our JVM or somebody else's JVM. What we don't have the just-in-time compiler overheads. We do have a just-in-time to support loading of classes that were not known in the compiler ahead of time compiler, right? But it's much less sophisticated than hotspot, and it has less memory overheads. We also have our own memory manager. We don't use hotspot memory manager or hotspot garbage collectors, which may, for some applications, give you much better results in terms of footprint. And one thing that we do, what most of hotspot garbage collectors do not, is we have some heuristics for returning the memory to the operating system. So it's more adaptive. So when your application needs a lot of memory, our memory manager will let it allocate if there is enough physical memory available. And when it gets collected, most of it, and it doesn't grow again, it will compact the heap and return this free memory to the operating system. And not all hotspot garbage collectors do. For instance, if you have like, I don't know, image editor, right, that needs to do some sophisticated processing that requires a lot of memory. On hotspot, it will allocate a lot of memory and it will remain this way, even if you then do some small edits. And in our case, that memory will be returned and you will get less data. But these are all this startup time, memory footprint, performance, it all depends on the application. So when our prospects ask, will I get any of this? We say, this is a trial version, it's 90-day trial. It has all functions of the most expensive edition. Give it a try your application against it. If you see the benefits, we can talk about the price. If you don't see the benefits, well, it's not the case. Many companies do see the benefits. And then apply a solution. I actually tried to invite one of our customers to this event. We have a customer near Barcelona, but he wrote back that he's traveling at the moment.
Okay.
Okay, thank you.
Thank you very